Okay, here is today's lesson, and today we're doing about AC and DC. It's the start of what I call electrical circuits 2, mains electricity. So, in today's lesson we'll be looking at the difference between AC and DC. Know that what we call by mains is AC, and know the frequency and potential difference of mains. So I'm just going to date here today. So you should be doing the same in your booklet as well. And let's have a go at doing this starter. So please, you should be able to do the starter now because we've just done this in Electricity 1. So have a quick look at that, please, and see if you can do it. Hit pause now. Okay, so let's have a go at doing it. Here I've got a bulb has 0.218 kilocoulombs flow through it in 5 minutes. The PD across the bulb is 6 volts. So there we go. There's the charge, time, and voltage. So that's Q, that's T, and that's V, potential difference. And we've been asked here to find the current, which is I. So hopefully you should know that the formula you're going to use here is Q equals I T. That's not the format we're going to use though to solve it because we're trying to find I. So over here at the side, Q equals IT. We're trying to find I. So I equals Q over T. Now I can do this in too slowly, or do it in different ways, but 218 kilocoulombs, that's 218, that means 1,000. So actually that's actually 218 coulombs. 5 minutes needs to be turned into seconds. That's 5 times 60. So I'm just going to do that in my head. 5 times 60 is 300. So it shows me the answer is 218 divided by 300. And that comes out at 0.726. 0.726 amps, or as I often say, and I keep on repeating, 0.276 coulombs per second. Never get tired of explaining that. Okay, so you might have noticed the bulb resistance. So here in this question, they gave us some extra information that we didn't need. We didn't need the voltage to know what the current was, because current is rate of flow of charge. So we just need the charge and the time. So here's why they've given us that extra information, because they've been asked to calculate bulb resistance. So at the side here, if you're going to be doing resistance, you're very likely going to mean Ohm's law. Ohm's law is V equals IR, and we've been asked to calculate here R, and R is V divided by I. So we can do that. R equals V divided by I. What was V? Well, V is potential difference. V in this was 6. 6 divided by the current from before is 0.726. 6 divided by 0.726 equals 8.26. 8.26 ohms. Very good. So what are we looking at here? We are looking at a simple cell. It's only got a cell here in a circuit with a bulb and a switch. At the moment, the electrons aren't moving, so let's get them moving round. And now they're starting to go round counterclockwise. Now you also notice down here, I've also got a voltmeter, which is measuring the voltage here. And that voltage, you can see, is much about 16, 17 volts. So what would happen if I swapped the cell round? So let's reverse that round. And we can see the voltage has swapped round down here. And also the electrons have started moving round at the other direction. This is because batteries and cells are direct current and just really push the electrons round one way. But that's not the only way to do it. So that makes the question, what actually is AC? Well, to try and show you what AC is, I'm going to remove this cell here and I'm going to replace it with an AC component. And what do AC components do? Just take a look and see what's happening at the moment. You can see the bulb is flashing, and that's because the electrons, instead of just being constantly pushed through one way like they were before, they are now being pushed forwards and backwards. In effect, if you do this fast enough, it doesn't really matter because you can still transfer the same amount of energy to the bulb. There are some advantages to doing AC, but really that's not what we're concerned about here. What we're concerned about is actually what AC is. And AC is just really where you're constantly changing the voltage so that the electrons change direction. I can even show you what the current is doing by putting on this chart here. And the current is pretty much doing the same thing. A couple of features about AC. Well, one, I can increase the voltage, and that's just going to make those peaks bigger. Can you see? And the other one I could do, you can't really do this in DC, is you can change how quickly it changes direction. So I've taken it up to the maximum here, which is just 2 Hertz. And you can see the electrons are changing direction twice a second. You won't really notice this in the mains because the frequency of the mains is 50 Hertz, which means the electrons change direction 50 times a second. So there you go. And this is called alternating current. So having seen the FET demo, what can we say about these two graphs? Well, potential difference over time. Well, we know AC does something a bit like this. The potential difference goes forwards and back, forwards and back. This is actually called a sinusoidal wave. Doesn't need to be perfect if you asked to draw this, but just the idea, this means the electrons are moving forwards and then back, forwards and back. A DC current would normally look like a nice straight line. In effect, this is saying that the electrons are being pushed forward at this constant rate. This would mean a constant current, and this would mean an alternating current. Okay, AC. What does AC stand for? AC stands for alternating current. AC, right, in AC, in the mains, what does that mean? Well, in the mains, you need to know that the mains has an alternating frequency of 50 Hertz. That's the frequency. So that means it changes direction of the current 50 times a second. The potential difference of the mains is about 230 volts. What does DC stand for? DC stands for direct current, and that's just current flowing in one direction. What we're looking here, that will be coming out of things like cells and batteries. They all provide. Okay, just to finish off this lesson, okay, could you maybe draw a diagram to describe the movement of electrons in an AC? So that's up to you to come up with your own way to represent it, so you remember yourself what was going on in that FET animation. And just one more slide here. Direct current. Direct current is that flows in one direction. We should know that now. Where do we use direct current? Well, on circuit boards, generally they don't really like AC. We use AC for transmission of electricity, but most of the smaller devices that you'll use actually use DC. They might plug into AC, but they normally have these little devices in between, like in a computer, where you can actually just change the AC, or it might even be somewhere on the circuit board they'll do that. But most electronic devices operate with DC. Okay, that's the end of the lesson. Bye.